Okay, week 5, and today we're going to be getting into renormalization group. So let's revise where we were last week. So last time we talked about how mean field theory breaks down, and we discovered that near the critical temperature, its mean field theory predicts that it must break down. And so we know that means that we have to take into account spatial variations and spatial fluctuations in our description of the system. And up to now, we've never had to do that. So then what we did was we introduced a coarse-grained description of the physical system. So if you look over here, there's 3 levels of description on the left-hand side. One is a microscopic level of description with all the spins. On the bottom is the thermodynamic description, where there's a uniform magnetization spatially not fluctuating at all, not varying at all throughout the system. And then in the middle is a coarse-grained description of the system where you average over a bunch of spins locally, and then you slide your window along in space. And so now you have a description of the magnetization as a function of space, now as a smooth function, which means it's differentiable. You can use calculus and so on and so forth. And we defined what that looks like. And that answers the question. If you say to me, well, here's some coarse-grained description of the system, and you scribble some curve in space, like the one I scribbled over here, what is the probability that we see that in thermal equilibrium? And the answer is, well, we just do like we did in microscopics. You have a Boltzmann factor, but now you have a different energy, not the microscopic Hamiltonian, but a thing that I'm calling the Landau free energy, which is the effect of Hamiltonian that governs the variations of the system on the scale lambda, which was the size of our coarse graining window. And then we wanted to understand how do we calculate that. And we talked about how we can think of this as being a sum over all possible functions, m lambda of r. And I gave you some idea about how one defines that in terms of Fourier coefficients. And then we wanted to know how we can calculate this. And what we said last time was, well, we can write down what the free energy is that gives rise to the equation of state. So that's step 1 over here on the left-hand side. We know the equation of state because we worked it out from our 10-second theory. We can then work out what should be the Landau free energy that corresponds to that. And it's something with a quadratic term in magnetization and a quartic term. And then at the end of the lecture, we started talking about how do we include spatial variations. And we need spatial variations because the Landau free energy is a scalar. It's going to depend on spatial gradients of the magnetization, but it also needs to be rotationally invariant and symmetric, because we expect that on very large scales, we don't really see the underlying lattice, we just see a continuum, and so we would not expect to see anisotropy due to the microscopic lattice. And so we would think that on large scales, symmetry is restored. And so we wrote down that the term that is the lowest order term in spatial gradients must involve gradient of m. But gradient of m is a vector. So then we made a scalar out of it by grad m dot grad m, and therefore we can put that into the Landau free energy. So let's just review that. So what we said then was that, just to remind you, so then I wrote down what you see over here on the right-hand side, that the Landau free energy, I don't just simply make m a function of r, I also have to include the spatial variation. So grad m squared is a scalar, but the thing I want you to notice about it, you might say, somebody asked at the end, why grad m squared is isotropic. And the answer is, I said this in words, but I didn't show you the algebra. If you take the integral of grad m squared and do integration by parts, so you can use the vector identity, the divergence of m grad m, that is equal to grad m squared plus m del squared m. And then if I do the integral of that, then the surface term is going to be the divergence. That just is then, from the divergence theorem, just becomes the integral of m grad m over the surface. And if we assume that the system is spatially has got periodic boundary conditions and all the spatial variations go to 0 to infinity, then all that ends up is that the grad m squared is equal to the integral of m del squared m. And del squared m is a rotationally invariant because it's just d2 by dx squared plus d2 by dy squared plus d2 by dz squared. And so this is a rotationally invariant scalar. So that's how we can write down our Landau free energy. And so this is the full form shown here on the right-hand side. What we have is a coefficient gamma, which tells you how strong the spatial gradients are. Like if I have a certain spatial gradient, how big a change does that make to the energy of the system? And then I have the second order term, the fourth order term with coefficient for the second order term that changes sign at the critical temperature, and the coefficient of the quartic term being always positive so that the free energy is always bounded below. So what I want to do now, I want to start off by trying to make a bottom-up approximation for what the Landau theory should be. So I want to show you that what we just derived on the basis of symmetry, phenomenology, top-down reasoning can also be derived from bottom-up. So what I've written over here at the bottom of the page is the Hamiltonian for the nearest neighbor Ising model in 0 external field. And I've written it as a quadratic term, SISJ, multiplied by some matrix Jij. And if you have a nearest neighbor Ising model, then Jij would be 0 unless I and j are nearest neighbors, in which case it would just be the scalar j. I could make it even more complicated and make it that Jij is non-zero up to some range r, or could even have some spatial variation. Well, for now, we'll just keep it like this. So then what I can do is I can think of writing down the local magnetization. So I can think of m sub I is the average of the spin I at site I, and this local magnetization will eventually this local magnetization will, when we take the continuum limit, this will eventually morph into m as a function of r, coarse-grained at some scale at lambda. So that's what we mean by our local magnetization. And so I'm going to write down now how does the interaction term depend on this variable. So what is our goal? So what we're going to try to do is we're going to try to express the Hamiltonian in terms of these MIs as is something like the Landau free energy. That's what our goal is, and we're going to just here focus on the gradient terms, not the other terms. So let's see how we can do this. So I'm going to write it down like this. The term I'm interested in is summing over I and j, the matrix Jij, Mi, Mj. And I'm going to write this down as follows. So first of all, I'm going to assume that I'm on a lattice. So I'm on a lattice with lattice spacing A, like so. So that's our lattice. And then I'm going to write this down as follows, and then I'll explain to you what I've done. So first of all, I'm going to sum over all sites on the lattice I, and then I'm going to sum over all sites on the lattice which are within range of that lattice site I. So you can think of this like as follows. Here is my lattice site I, and then I've got some neighbors of that site. Those neighbors might be this one, the nearest neighbor, this one, and this one, or they might have a longer range, and there'd be other sites that I would need to include. But in any case, what I'm going to get then is because I'm summing over both I and then j, I'm going to get two terms that go like j. So I'm going to have j a squared over 4. And you'll see where this j a squared over 4 comes from. And then I'm going to write down what comes in here. So first of all, I'm going to write this as m at the lattice side I plus delta minus mi over a squared minus mi plus delta plus mi over a squared, like that. So that I claim is an identity. All I've done is I've added and subtracted terms. So let me just make sure you understand that I is the site in yellow, and then the vector delta is either this vector or this vector or this vector or this vector, the nearest neighbor vectors to the vectors to the nearest neighbor sites. Okay, and then so if you expand out these squares, mi plus delta minus mi squared, and so on, you will see that it ends up being exactly on the right-hand side. Now, why did I do this? Well, it was a clever trick, because this term over here, looks like a spatial gradient. So I can say that, and this term over here is just m, basically 2m squared, something like that, because it's m at the side I plus m at the side I plus delta. It's roughly the same thing. So that's basically not a spatial gradient. That's just a constant. But this first term is a spatial gradient. So I can write all of this as minus j a squared over 4 times the sum over all the points on the lattice, then the sum over the neighboring sites of mi. Well, let me write it like this. So this is just m of at site R plus all the nearest neighbor vectors minus m like that, and so I can expand the term in the brackets, so that then becomes minus j a squared over 4, and then the sum over I, then the sum over the nearest neighbor, the vectors to the nearest neighbor sites. And then if I do a Taylor expansion of m of Ri plus delta, m of Ri plus delta is just the vector delta dotted with grad of m evaluated at R of I, and that's divided by A, and then that's all squared plus order m squared, which I'm going to probably get bored writing all the time. And then if I write this then as a continuum, then this thing is equal to minus z j r squared over 4 times the integral d dr over a to the power d grad of m of r squared plus something of order m squared, which I don't care about. And so I can think of this as being, this is gamma times the integral of grad m squared ddr. And I can read off what this coefficient gamma is. So this gamma is equal to r squared j, the coordination number on the lattice, for a to the power d. So this then is exactly what we had over here. So if you look over here on the left-hand side, what we had written down phenomenologically was this. And so now what I've shown you is I can motivate that by just starting from the Ising model Hamiltonian, and in a fairly, not rigorous, certainly not a rigorous way, but in a straightforward calculation way, see that the term that I must get in the effective free energy should be a term like that. Okay, so that's the that is my that is what I want to say. What I want to say then about the Landau free energy and how we construct it. So now I want to start moving on to a renormalization group. So so we're going to talk about renormalization group, and this is in chapter 9 of my book. And what we're going to do today is we're going to follow section 9.1. We're going to basically introduce the renormalization group, and we're going to give you some idea of the philosophy of it and what we're trying to achieve. We'll do a very heuristic description of it, and I'll show you what we can end up calculating. So let's just sort of summarize what are the ingredients that we've learned about so far. So the ingredients of our modern understanding of the normalization group are based on the following things that we've already seen explicitly in this course. So the first thing is we've seen that there is a diverging correlation length. When we're close to the critical temperature. We've seen that thermodynamic and correlation functions have a singular behavior, perhaps even non-analytic behavior. We've talked about the idea that there are multiple levels of description, and we've even started to see how we can be conscious of those levels of description and actually use them in how we think about describing phase transitions. So the question that we're going to try to understand, what is our goal? What we want to understand are where the singularities come from, we want to understand why are the critical exponents and scaling functions different from mean field theory. And our starting point is going to be the observation of data collapse which really goes back to Ben Widham and Leo Kadanoff in the 1960s. And it was this observation that started Kadanoff trying to figure out how to make a multi-scale description of statistical mechanics, and he developed the description that we're going to be using. So the history of this is a data collapse was empirically observed. and then really done by both Widom and Kadanoff. And then what Kadanoff did was show that this implied a sort of universal scaling form, which we already have derived, but he derived it in general. He showed how that follows from the idea of looking at the effective Hamiltonian of a system on different scales. And so this is known as the Kadanoff block spin picture. And what he was able to do was he was able to then derive data collapse scaling, and also scaling laws between critical exponents. And we saw earlier on in mean field theory that if I take the critical exponent for heat capacity alpha, I take the critical exponent for the order parameter beta, and I take the critical exponent for the susceptibility. And if I make the sum alpha plus 2 beta plus gamma, I always get 2. And we can derive that now, or we will be able to derive that from Kadanoff's assumptions. So he was able to derive those things, but he didn't really finish the job. So Kadanoff did this by making a variety of technical assumptions, which we'll talk about. And then later, what Wilson did was he systematized the whole thing. And that was the birth of the renormalization group. So Kadanoff's technical assumptions, what he was able to do was explain scaling laws, explain data collapse. He was not able to calculate critical exponents. So this but no values of critical exponents. And so Wilson was able to calculate the critical exponents, calculate everything. So that's the history of it. Now it's not just these people. There are other researchers around the world who are doing things at virtually the same time in different ways. In the Soviet Union, Paczynski, Pokrovsky, in Europe, and so on and so forth. I'm not going to list all of the names. Jonah Lucinio, for example, in Italy, and other people. There's references in my book on this. So, but these are the people generally regarded as the main advances that contributed to the development of the subgrid. Okay, so let's now get into the calculation, and so let's talk about the basic idea. So the goal in this section, the goal is to calculate the singular part of the free energy. And I'm talking about the free energy for spin. So we'll talk about the free energy, which in principle is a function of temperature and external field. Now I want to make sure that you understand exactly what I mean when I say the singular part of it. So let's draw this picture. It's quite an instructive one for people to see. Let's suppose I'm not looking at the free energy itself, I'm looking at its second derivative, the heat capacity. So you might say, well, we've heard that the heat capacity diverges, so that presumably is a very, very big effect. So let's actually see what the data really look like. So you may have over here the critical temperature Tc, and then you may have some background heat capacity that looks like this, and then the singular part of it is just in this vicinity of here. There's going to be some little blip like this on top of that. So what we're going to be doing now is we are essentially going to be zeroing in onto this part, and this divergence to infinity is on top of a background heat capacity that is smooth and regular as we go through TC. So we only care about the singular part, and so I'm going to write that in terms of the singular part of the free energy, which we'll think of as being depending on T and depending on H, where I mean by H over KBTC, and T is T minus TC over TC. Okay, so what is the basic idea? So if we take a look at our physical system, we know it looks something like this. It's basically a box. It has in it sort of correlated domains. Something like that. And we can think of this as being a background of spins that are down. And then on top of that are these spins that are pointing in the up direction. And so we want to know, so these blobs are of order the correlation length. And we know that the microscopic lattice is much smaller than the correlation length. And so what we're going to try to do is we're going to say let's make little blobs of size, not the correlation length, but smaller than the correlation length, but still much larger than A. So what we're going to try to do is we're going to try to group spins into blocks of size LA, given like this, and then we're going to ask the question, what is the effective Hamiltonian for these blocks? So that's the idea. So if we were to zoom in onto one of these correlation length blobs, so here is our drawn up, here is our correlation length scale blob. So let's say that this is the correlation length like this, and then underneath this is the microscopic lattice. So there's a microscopic lattice like that, and on that microscopic lattice are all the actual spins. And then what we're going to say is, well, on this microscopic lattice, what we're going to do is we're going to make little blobs. So let me say, for example, here is a blob So this is a block of spins, and this size here is what I'm calling LA, like that. And so there's a bunch of spins in this block, and we're going to ask what is their effective behavior. So basically what we have is L to the power D spins in a block, and we want to calculate what is their behavior. Now the point about this is that these block spins are the block size is much smaller than the correlation length, and so what that means is that basically we expect that all the spins in the block are strongly correlated. So that's what we expect. All these spins are more or less behaving in unison. And so what we're going to try to do is replace all of those spins by just one single representative spin. So that's going to be what we want to do. That's our goal. So we're going to ask how we define that, and we're going to ask then what is the Hamiltonian that governs that behavior. So let's have a look about what we mean. We're going to work explicitly in 2D. So for example, if I had a spin like this, so I've got L equals 2 in this direction, L equals 2 in this direction. So this is a block spin. It has how many spins in it? Well, it will have L squared spins in 2D, and L is going to be 2, so that's 4, and so on. So the block contains L to the D spins. Okay, but in the total system has n spins. So how many blocks are there? Well, we know that there's n original spins. And so that means that there are n over L to the D block spins. So we're going to label the block spins, label the blocks by I, capital I. So that's going to go from 1, 2, all the way up to n L to the minus D. And the microscopic spins they have little I, which is 1, 2, all the way up to n. Okay, so here's how we're going to define a block spin. So let me write it down and then convince you that it makes sense. So what we're going to say is that the block spin has the following definition. We're going to say that it is, excuse me, I take all the spins that are in the block I, and I sum over all of those, and then I'm going to divide by the magnetization per spin, so I'm going to call that ML bar, and then L to the D. So why do I define it like this? So so how many spins are there? There's L to the D of them. They each have a net magnetization per spin of ML, M sub L. So this is the net magnetization per spin of the block of size L. And so then, so I can write then that M L bar, how is that defined? So I take all the spins in the block I take their microscopic average with the Boltzmann distribution, and I divide by L to the D. So this is the magnetization, the average magnetization of the spins in the block I, and then if I were to compute what this is, so then what this means is that if I then compute the expectation of SI, it's going to be sum over I equals from all the spins in the block I, SI, and then divided by the magnitude of the spin times L to the D. And so this is going to be either plus or minus 1. So I average over the spins. They could all be plus or minus. So when I average them, I'm going to get plus or minus 1. And so these block spins behave like the original Ising spins. So the block spins by construction resemble the original microscopic spins. Okay, so that's good. This is just the way that Kazanov did it. Later, we don't have to do it in quite a contrived way. So then the next question we want to ask is, so the question, what is the Hamiltonian? So we already mature enough to know that we should think of this as an effective Hamiltonian. What is the effective Hamiltonian that governs the equilibrium statistical mechanics of the block spins? So the answer to that is we don't know. We don't know how to calculate it, but later we will have a calculation. So what we're going to do is we're going to make assumption number 1. Well, assumption number 1 is that at the microscopic level, what we had were nearest neighbor interactions. And so what we're going to assume then is that, and I'm going to put question mark, that suggests that the block spins also interact only with their nearest neighbors. So that's a very powerful assumption, and in fact, it's completely wrong. But that doesn't actually matter, and that was the great thing about the renormalization group. is that it enables us to understand why this assumption works. So I'm just going to say, just as a comment, that the comment is that this is actually wrong, but doesn't matter. Well, it kind of matters, but it doesn't matter, and we will see that later when we do this more systematically. Okay, so but why is this assumption such a powerful assumption? Well, what this assumption means is that means that the block spin Hamiltonian will have the same form as the original microscopic Hamiltonian. So it'll have nearest neighbor interactions and it will also interact with an external magnetic field. So I'm going to write it down in the following way. So we can see that the Hamiltonian on the scale L, we're going to write down just as we did for the Ising model. So it's going to be the sum over nearest neighbors of the block spin SI interacting with block spin J. And then there's going to be an interaction with the external magnetic field. So we'll say that the external field then has a value H sub L, and then we sum over the block spins themselves, and this sum goes from 1 up to n L to the minus D, and the same thing here, like so. And then there's going to be a coupling constant in here. So I'm going to call this coupling constant K sub L. So KL is J over KBT, but now at the scale L. And so this then is our description for the effective Hamiltonian on scale L. So let's now so that's our first picture. So we can summarize this in the following way. So remember last time we talked about a range of descriptions. So we have on the macroscopic scale, we have thermodynamics. And then we said, well, at the microscopic scale, we have our Ising spins, and then we have trace of those Ising spins over the degrees of freedom SI. And now what we have in the middle here is the trace over the block spins of our Hamiltonian on the scale L. And when we do all of these traces, they must all end up giving us the same description. So this is micro, and then now this is the coarse-grained description. Okay, so that's fine. And you might say, well, what did we do? Why is this interesting? Well, it's interesting for an interesting reason that comes to us from dimensional analysis. So who cares? And the answer is, let's do dimensional analysis. And then we'll see. Okay. So the point about this is that the physics of dimensional analysis is that the physics, the end results that you predict are independent of the system of units that you use. So what does dimensional analysis tell us? It says basically that the physical results are independent of our units. Okay, that's a basic fact in order to be able to do physics. So let's have a look at the correlation length. Now we know that all the behavior in the system is due to the correlation length. And the correlation length is diverging. That is the length scale that then gives you the breakdown of all the usual effects. So the physical. So we can have here. Actually, no, I don't want L. I want psi. So we have here a physical correlation length, which is the thing you might measure. And then I might have, well, the original correlation length. So that might be, well, if I'm using the lattice spacing as my units, then I might say, well, there's some psi1 that tells me how many lattice spacings the correlation length is. So you might say, okay, I'm at this particular temperature, the correlation length is about 20 lattice spacings, so psi1 would be 20, A is the lattice spacing. Okay, so that gives me the physical correlation length, and if I know what A is in angstroms, I know what is the size of the correlation length. But I could also measure the correlation length in terms of my block spins. So in terms of my block spins, I could say, well, if I don't know that the length scale is a block spin variable, then I will say that I have the correlation length is going to be psi L block spins. So this is the multiples of the lattice spacing. And then this variable psi L would be measured in units of the multiples of the block spin size. Or if you like, the block spin separation. So if you then ask yourself, how do these things relate to each other? Since these things are equal, then I can then immediately see that this equation predicts then that the correlation length on scale L is effectively the correlation length on the lattice spacing, which I call psi1, divided by the scale L. So if you say to me, oh, it's 20 units in the lattice spacing, in my block spin variables, it might only be 5 units if the block spins are 4. Okay, so it's going to be a smaller number. And so, but now we know that the correlation length depends on temperature. But the correlation length depends on temperature. And in particular, it grows as we approach TC. So if it grows as we approach TC, then what that means is that since psi L is going to be smaller than psi1, then what that means is then effectively the temperature of the block spin variables is further away from TC than the microscopic variables. So what that means is that by doing the block spins, we're just grouping spins together, looking at their configurations, lumping them into blocks. Then I discover that in my units of my block spins, when I look at the system, it has the same Hamiltonian as the original system, but now the temperature seems to be further away from TC. So if temperature is further away from TC, then what that means is that the reduced temperature has got bigger. So what this then means is that there is a new effective reduced temperature. And that's going to depend on scale. So we'll call that T sub L. Okay, so by doing this coarse graining and looking at configurations, insisting that I use statistical mechanics to describe these blocks, what I find is that the Boltzmann factor that I must use must have a different temperature than the one that I physically have. It must be a temperature which is further away from TC. And so this T, it will call T sub L, and this is bigger than the original temperature T1. So we're further away from TC. Okay, so you might think, well, that's really weird. That's really weird. So there's now an effective temperature that goes along with coarse graining our system. Okay, now it's not just we get an effective temperature. There's more. So actually, we also get a change in the magnetic field. So we get a change in the magnetic field that effectively acts on the block spins. And the reason is because the magnetic field acts on all the individual microscopic spins, but its effect on the block spin might not be the same. So let's see how that happens. So how does the coupling to the external magnetic field change? So in a microscopic Hamiltonian, this is the term that we have. We have this is the the contribution to the effective Hamiltonian from the interaction of the external field with the spins. But we know how these spins are related to the block spins. So I can write this in the following way. This is just H times ML times L to the D times the sum over the block spins of S sub I. Remember that this came from the fact that the block spins are defined over here. In the following way. Here are the block spins over here on the left-hand side. And so if I know what the sum, so the sum over SI then is just going to be the sum over the big spins in this way shown over here. So then I can then say that this is then just some variable which I'll call HL. And then this is the sum over the block spins of SI. And so this is the effective an external magnetic field. And at scale L, and that is H sub L is equal to H times ML bar times L to the power D. Okay, so that completes our picture of what is the effective Hamiltonian for the block spins. So now we have the complete effective Hamiltonian for the block spins, and it explicitly depends on L. Okay, so now comes Kadanov's brilliant insight. So what is this consequence? We have H sub L on the for the block spins. We have our original Hamiltonian. I can call it H1 if you like, for where L is equal to 1. This is for the original spins. And these two things have the same form. Now, if they have the same functional form, that means something really kind of surprising. It means that the free energy of the block spin system must be the same functional form as the original microscopic system. There's only one difference. The only difference is that where we had H before, now we replace it by H sub L. Where we had T before, now we replace it by T sub L, telling you about the scale. And so if we translate that into an equation, what that simply says is that if I were to work out the total free energy of the microscopic spins, the singular part of the free energy at least, so we write that as N times the free energy per spin, that's FSTH. That must be the same as the free energy of the block spins. So they must have the same functional form, but now we replace T and H by TL and HL. And how many block spins are there? Well, there aren't any of them. There's only L to the minus D, N times L to the minus D. And because of this fact over here, this fact means that this function f sub fs and this function fs, those are the same mathematical functions. And so now we have a functional equation that relates these two, the free energies of these two systems. So this is a functional equation for the function fs as a function of its two variables, x and y. And the factors of n cancel, so those cancel out, and so we get that fs of TL and HL is equal to L to the D times the free energy per spin of T and H. Okay, so that's as far as we can go with this analysis unless we make it one more assumption. Okay. So since we don't know how TL and HL vary. And so we make a second assumption. So assumption number 2 is that we know that T is getting bigger as we coarse grain the system, so it's an increasing function of L. So we're going to say that this is a power law function of L. So we're going to say that it scales like this, and we're going to say the same thing for H, that is, it is equal to the original H times L to the YH, and we're going to say that YT is some number that we don't know, that's greater than 0, and YH is some number that we don't know, which is greater than 0. Okay, so we're going to assume this, and why? Well, we're trying to understand power law behavior. So Kadanoff guessed that this might be what's going on. And we're going to see later that this is true. And we're going to see this from the renormalization group. Okay, all right. So let's plug that in. So now we've got the formula that Fs of t as a function of h is equal to L to the minus d times Fs of t L to the y sub t h L to the y sub h. So we don't know what y and t, what these are, and we're going to see that this equation is a very powerful equation. So this again is a functional equation, and so what we want to do next is we want to figure out how to solve this. So we're going to solve this, but we're going to take advantage of a special feature, and that is we didn't say what L was. So note that L is arbitrary. Okay, what we said was, well, I start off with our microscopic lattice spacing. I have some L, which is much larger than that, but still much smaller than the correlation length. And as I go towards the critical temperature, the correlation length must diverge and go to infinity. So it's very easy to satisfy these inequalities. So as we get closer to TC, there is a huge range of L that satisfy this condition. And what that means is practically, we can choose L to be whatever we want because the answer should be independent of L. So choose L as we like because the results should not depend on it, or should only be weakly dependent on L. As in this picture, not at all. Okay, so everything we're doing now, this equation in the yellow box, that equation, we've derived it by making these two assumptions. But later we'll see that we can derive this equation from the normalization group. So what we're going to see then is now I'm going to show you the argument that we'll use in the full normalization group that says once you've got this equation, how can you use it to make predictions? So now I'm going to show you how this equation makes predictions. So the above is derived from the full renormalization group, which we haven't done yet. But the next steps are the same, and they involve some tricks. I'm going to show you what those tricks are. Okay, so what all these tricks amount to the following. We're going to exploit this arbitrariness. Well, this indeed is an intrinsic feature of the normalization group. You may wonder what group means. A group is a set of transformations. In the case of the normalization group, those sets of transformations are transformations that coarse grain the system or maybe shrink the system. So what we're going to see, in fact, that there is a group of transformations, and the result does not depend on what the L is. And in fact, we'll see that we can derive the equation in yellow from this group property. So it is this arbitrariness that is then says that this is related to the group aspect of the normalization group. Okay, so we'll see this later. So it's basically a symmetry. And if it's basically a symmetry, then I can think of the generators of that symmetry. Those are scale transformations that change the system from one scale to another. So here's what I'm going to do. The first thing we're going to do is we're going to choose L to be the absolute value of t to the power -1 over y sub t. Okay, so that's my first choice. Okay, you may say, wow, that was really obvious. Why would I want to choose that? Okay, it just seems like a very complicated choice. Well, let's suppose we choose that. Then, excuse me, then L to the power y sub t times the absolute value of t will just be 1. And so what that means is that if I look at Fs as a function of t and h, we know that this equals L to the minus d, as shown here on the left, but now I've got to replace L by this formula here. So what I get is t to the power d over y sub t times our original function. The first variable is 1, and the second variable is h, absolute value of t to the minus y sub h over y sub t. So by choosing L to have that particular value, so the game is you tell me what the relative temperature is, and some number. You tell me what L is. Well, I'm going to choose L to be this number. We suppose I know the numbers y sub t and y sub h, which in the normalization group we do. And then what I have is that this function of two variables is now a function of one variable. Because this function here, I can write this as just some f of h over t to the power y sub h over y sub t. And f of x is fs of 1 and x. So this 1 is just a number. So I evaluate this two variable function with the first argument being 1 and the second argument being this combination of h and t with some powers. And so now what I've derived is the following. I'm also going to define a new variable, which I'll call capital delta, to be the ratio of yh over y sub t. I'm going to define 2 minus alpha to be d over y sub t. And then what I've just, then in terms of those new definitions, what I have is that the singular part of the free energy at T and H is equal to absolute value of T to the power 2 minus alpha times some function, which I don't know what it is, but it just depends on T to the power delta, like so. And this is data collapse. Because I've got a function of two variables, function of T and H, actually, when plotted in the right way, will then be just a function of one variable. So we can see this. If I were to plot say the magnetization, I calculate from this against H over T to the delta, and this divided by T to the power beta, all the data for different T's and H. All collapse onto two curves. This might be T less than 0, and this would be T greater than 0. And so what I've shown you then is that by making these assumptions, what we've actually derived is the scaling hypothesis. And we've derived it. I'm going to put derived in quotes because we don't know what y t and y sub h are. They're unknown here, but later they are calculable in the normalization group. And we'll see that later on. Okay, so that's data collapse. So we can see that we can derive this by making various assumptions, and those assumptions we can later understand in more detail and more precisely by renormalization group. Okay, so now I want to end by showing you that we can derive scaling laws. So let's start off with this particular form. And this f can be a different function for plus or minus. I'm not going to always remember to write that. And so what is our goal? I want to derive alpha plus 2 beta plus gamma equals 2. So let's work out how to do that. So first of all, if I want to compute the magnetization, well, that we know is just minus 1 over kBt times dfs by dh. And so that is equal to 2, so t to the 2 minus alpha minus delta times the derivative of this function f prime as a function of h over t to the power delta. So there's 1 over kt comes from the fact that I divided the external magnetic field by kt to go from big H to little h. Now, we know that this must be going as t to the power beta, and so that tells us that if this is going to be true when h is equal to 0, then that means that the scaling function f prime, evaluated at its 0 argument, must be some number like 3 or something like that. And so that's the first thing, and then we can read off that this exponent beta must be related to this exponent alpha and this exponent delta by this formula here. So this thing over here must this thing here must be the same thing as that. Okay. So that's the first point. So now let's suppose we compute the isothermal susceptibility. So that all we have to do is just do one more d by dh. So chi t is equal to t to the power 2 minus alpha minus 2 delta times the second derivative of the scaling function evaluated over at h over t to the delta. And as h goes to 0, chi t goes as t to the minus gamma. That's the scaling law that we've seen before. And so therefore, we can say that these two things must be the same. So gamma 2 minus alpha minus 2 delta is equal to minus gamma. And then we also have this previous equation over here on the previous page. So if we eliminate what happened here? Why is that? No. Why is it that, I don't know why that line is there. I'll fix it later. If I eliminate delta, then I get that alpha plus 2 beta plus gamma is equal to 2. And that was the scaling law known as the Rushbrook scaling law. So these critical exponents, so let's just summarize then. So Kadanov's block spin argument idea plus 2 assumptions gives data collapse, and it gives relationships between critical exponents. But it doesn't give us what those exponents are, and it doesn't justify what are its assumptions. So next time we will continue with this, and we're going to elaborate a bit more on these over normalization group constructions. Okay, so we will stop there. Let me just turn off the recording, and then I can take some questions.